Okay. So this is homework 3.2, number 12. So we want to evaluate that. We have the square root of the sine. We have cosine cubed. So the sine is an inner function here, so I'm thinking it would be a nice u. And if that was the case, what would be the du? Cosine, right? But I have too many cosines, but I can fix that. So what I'm going to do is I'm going to rewrite this. First, I'm going to call that sine of x to the power 1/2. And then the cosine I'm going to break up as a cosine squared of x times the cosine of x. Because then this is my future du right there. Now I just have to get rid of this cosine squared, and I got the Pythagorean identity to do that. So I'm going to replace the cosine squared with 1 minus sine squared. So now I have the integral of the sine of x to the power 1/2 times parentheses 1 minus sine squared from the Pythagorean identity, right, replacing that cosine. And this cosine is just chilling out on the edge. And I'm just going to leave that alone there, okay, because I'm going to need that. Come on, color. There we go. So I'm only going to distribute the sine to the 1/2 through there, okay? So now I have the integral of sine to the 1/2 of x minus, now I have the same base, sine times sine, so I add the powers. 2 plus 1/2 would be 5/2. My arithmetic okay so far?
Yes. I don't know.
All right, so now I'm ready to do my u substitution. So here I'm going to let u, I'm going to write it up top, equal the sine of x, and then du is the cosine of x. And so I just go through and substitute stuff. And this works out pretty nice, I think. So this gives me the integral of u to the 1/2 minus u to the 5/2, and then there's my du right there. So this is definitely a hard problem. I only knew what to do because I did it before, right? After I failed 2 or 3 times. All right, antiderivative. Add 1 to the power, right? So that's going to give me u to the 3/2. And then we divide by 3/2 or multiply by 2/3. Add 1 to the 5/2, and we get u to the 7/2 times 2/7, and we get a plus c. And then I go back and drop the sign in. And then the fun part is typing this into the little box in my open math. So the way I would express the answer would be 2/3 parentheses sine of x, close parentheses, raised to the power 3/2 minus 2/7 parentheses sine of x, close parentheses, raised to the power 7/2, and then plus c. So I think that's the safest way to type it in my open math. If I'm unsure about that, what do I do? Take its derivative and see what happens. Now, the downside of that approach is to get to this point, we had to apply a trig identity, right? So it's not going to quickly get me back to the answer I started with. But what I could do is take that derivative, graph that result, compare it to that graph, and hope they match. Okay, so we could do a graphical check. Carter?
So how do you get the sine to the 5/2 from applying sine to the 1/2 to sine?
Yeah, so basically, good question. New page. So I have sine to the 1/2 of x times sine squared of x.
Okay. It's powers.
It's just the power rule, yeah. So I'm multiplying things with the same base, so I just add the powers.
Yeah. All right.
Okay.
What's up?
You know, back to y is number 17 and 3.2, and I did a similar questions, like a completely different question.
I don't know.
It's a differential equation.
Oh, yeah, sometimes they cycle through applications. So that one picks a few different applications.
We actually go back to the third one.
Not this one,
It's the
this one. Yeah, that's a good problem. I'll take a look at that one. Number 17, you said?
Yeah.
Okay.
I don't really know what one.
Okay, so 17. Yeah, I did want to do one of these applications.
Okay, that's the one I first had.
Okay.
And I didn't get it.
Okay, and then I gave you a very different one?
Then it gave me the link for on Sine from.
Yeah. So, yeah, so this one right here is basically an application of the fundamental theorem of calculus. So to undo a derivative, we integrate. Okay. So we would just integrate both sides of this, and then I can figure out what C is because they gave me when X is 0, Y is also 0, so I can calculate what C is in this case. So we did some problems like that way back in chapter 1 when we looked at the fundamental theorem of calculus. So just quick setup on that one, and I'll see what else I can get. So let's see, what was that one again? It was the cosine squared 0, 0. So I have the derivative of y with respect to x equals the cosine squared of x, and I'm asked to come up with y, and also that the original function f of x had the point 0, 0. So in other words, f of 0 equals 0. So that information allows me to find c. So the fundamental theorem of calculus says if you integrate a derivative with respect to x, they pretty much undo each other and you get the function. On the other side, I have to figure out, okay, then what is the antiderivative for the cosine squared of x dx, which we did that one in class the other day. I'm going to get an answer plus c, and then I just plug in 0 on each side to figure out what c is. Okay. So I'm not going to repeat that one again. What formula would you use? Does anybody recall? Double angle formula is what you're going to use to evaluate that. Yeah. So this is just a substitution with a trig identity. Solve that one. So remember, the double angle says that the cosine squared of x is equal to 1 plus the cosine of 2x over 2. And that's an identity that's going to come up over and over again.
Actually, I meant to say half angle.
Yeah, the half angle and double angle formulas are essentially the same thing. They're just looking at it in two different directions. Okay, so you said you had a variation that had arc length. So let's see if I get this wrong. It'll give me a new one eventually. Try some more problem, and this one gives me arc length. All right, so the natural log of the cosecant of x. Sure, let's set up arc length. That was one of the problems for a similar problem from the last area. So I'm just going to set it up. I'm not going to finish it. Setup's the hard part. Let's cut that page. Okay. So formula for arc length. Remember, that's just the fancy Pythagorean theorem for calculus. So it's the integral from wherever you start to finish of the square root of 1 plus your function's derivative squared with respect to x. So we got to take the derivative of the natural log of the cosecant of x. So let's see. Derivative with respect to x of the ln of the cosecant of x. Okay, so this involves the chain rule. What's the outer function? Natural log. So derivative of the natural log is 1 over whatever's inside. What happens to be inside is the cosecant of x. Then I have to take the derivative of the cosecant, which isn't one we do often. Does anybody happen to remember that one from way back?
Negative.
Negative?
Negative 1 over
1 over.
Okay, what's the derivative of the secant?
Cosine.
No, that secant is 1 over
Oh,
cosine. What's the
secant.
derivative?
Secant tan.
Yeah, so this is like that one. So if secant is secant tangent, cosecant is cosecant cotangent, but it's a co-function, so it gets a negative. Yeah. So then I multiply by the negative, cosecant cotangent. Yeah, and that's one you could look up if you're stuck on it. And that's one we could put on our cheat sheet of stuff. So cosecant cotangent. Okay, so that's the derivative. Does it clean up a little bit? A little bit. So the cosecants cancel, so I get negative cotangent. That's nice. It's not too bad. So for the arc length formula, what do I do next after I find the derivative? Square it and add 1. Okay, so just if I look at the inside here, I'm going to get 1 plus, oh, what's going on with my pen? Squaring a negative gives me a positive, so I just get the cotangent squared of x. And does anybody recall the Pythagorean identity for that one? It's equal to the cosecant squared, which that's very exciting
This and the square root.
because I need to take the square root of that, right? That's the next step in finding my arc length. So my integral boils down to the integral of the cosecant of x respect to x.
What was your plus one?
This is all inside the square
I
root.
see.
So this is inside the square root. 1 plus the cotangent squared is the cosecant squared. We take the square root of the square, and we get the cosecant. Now, this is partially true. Technically, the square root of a square is the absolute value, right? Okay. But if you look at the graph of cosecant in this region, it's up above the axis. So now you just have to find an antiderivative for that, which I'm going to leave for you guys to play with, if that comes up in your homework. All right, next, we're going to check out section 3. I think this might be my favorite. I hate saying that. One of my top 10 calculus favorites. Trigonometric substitution. Okay, so trigonometric substitution is just a special kind of substitution based on the Pythagorean theorem. And the Pythagorean theorem actually has sines and cosines hiding inside of it. Okay. With me? Maybe? Sort of? Oh, yeah. So, for example, let's consider I wanted to take the integral of the square root of 9 minus x squared dx. Now, if it was 1 over that, that's a derivative of a function we saw before, in which case I'd have an antiderivative, but it's not 1 over. Now you'd think, wait, if it's in the numerator, it should be easier, right? Okay. Well, we haven't solved this one yet. Okay. So we got to find a way to solve this. That's also the graph of a semicircle, which seems like, hey, it's a semicircle. That should be easy to do, but we haven't done it yet because it's hard. This is actually a chunk of the Pythagorean theorem, if you think about it. Right? So if you draw a picture of what that might look like, come on, there we go. If I draw a right triangle, let's see, the 9 could have come from squaring what? 3. And since I'm subtracting from that, that means that 3 must be the hypotenuse of a triangle. Okay.
Is it 2, 3, 4, 5?
Now, well, I don't know that, yeah, because I don't
It
have enough
can't be a 2, 3,
information.
4.
A 3, 4, 5, yeah. So x could be here or there. I'm going to choose it to be here. Hint, in these kinds of problems, never put x on the opposite side. Okay?
Never put it on the x-axis.
Never put it on the opposite side. You can.
Both up.
Oh, sorry. Here's my angle theta. So with respect to theta, that's opposite and that's adjacent. Sorry. Thinking trigonometry here.
Right. I think you said that backwards.
I
Yeah.
did. Adjacent side. Never put it on the adjacent side of the angle.
Everyone. Hello.
Can you? Yeah, you can, totally. You can do anything you want in this world, sort of, but there's consequences, right? So it's harder if you do so. Okay, so I'll remind you of that later. If that's a 3 and that's an x, Pythagorean theorem allows me to solve for this missing side. So it's going to be the square root of 3 squared minus x squared. Okay, so that's where it sits in the scheme of things. All right, now check this out. According to this triangle right here, let's see, the sine of theta, that's my angle, would be opposite over hypotenuse. Okay. Or I could rewrite that and say x equals 3 sine theta, which is like a trig way to do it, right? We scaled up by a radius of 3 instead of a unit circle radius of 1. Another useful thing here.
You're not supposed to be theta.
Isn't it?
Oh, I keep messing that up, huh? Theta, yeah,
think
that's
you said
important.
You said theta.
I said theta, but I wrote x. Now, similarly here, if I looked at what's the cosine of theta, got it right, in this picture, what's the cosine of theta in this picture? Over? Yeah. So in other words, I could say that that square root is equal to 3 times the cosine of theta. So couldn't I do a substitution here? According to that triangle, couldn't I just replace that square root with 3 cosine theta? I like that. Problem though, I got to get rid of dx. Here's how we're going to do that. That equation gives me dx.
Oh.
Take the derivative of this equation right here in differential form, and you get dx equals 3 times the cosine of theta d theta. Right? Derivative of x could be called dx, right, in differential form. The derivative of the sine is what? Cosine. And differential form needs a d theta over there too. So now I can also replace dx. Okay, so I'm going to rewrite this. Let's switch back to black. So this integral can be considered, according to this triangle substitution, the integral of this guy right there would just be 3 cosine of x.
Theta.
Theta, shoot, jinkies.
You're right.
Okay, so that's this substitution right here. And then this dx substitution says, oh, just put in another 3 cosine of theta. Whoa, that's a theta, not an 8. D theta, there we go. Okay. So new page, finish that off. So again, I started with the integral of square root of 3 squared minus x squared dx. I used that to build the triangle with theta right there. So I'm just going to summarize quick. 3 has to be there because it's got to be the hypotenuse. I would like x to be there on the opposite side, not the adjacent side, which puts the square root over here. That triangle leads to the identities that x is equal to 3 sine of x, theta. Correspondingly, dx must be then, according to that equation, 3 cosine of theta d theta. And the square root has to be 3 cosine theta. Okay, so that's what the triangle tells me. And then I just dump that in there. And so now I have the integral of, let's see, I had a 3 times 3, so a 9 times the cosine squared of theta. Theta. Yes?
Shouldn't that be cosine of theta times sine of theta? Because x equals 3 sine of theta.
We took
So-
the derivative of that.
Okay, hang on.
Oh.
So this right here is a 3 cosine theta, right?
Yeah.
And then dx is also 3 cosine theta.
Oh, okay.
So it turns out, although I'm using x equals 3 sine theta as my substitution,
Mhm.
I can kind of bypass it. So alternatively, to address Carter's concern about that, one thing I could have done slightly different here is I could have taken that 3 sine theta and put it in here for x. And then the Pythagorean theorem would clean that up for me. Does anybody want to see that on a side note?
Yes,
Can you
please.
do that afterwards?
So if I substitute that in for x, then what I'm going to get, so I'm saying x equals 3 sine theta.
Wait, how did you get that?
How did I get x equals 3 sine theta?
Yeah.
Back 2 pages. When I drew this triangle right here, the sine of theta is opposite over hypotenuse.
Yeah.
So that means sine is x over 3.
Oh, you just, okay.
Multiply the 3
Yeah,
over.
okay.
So another way to think about it with trigonometry, the radius just scales the sine function up or down, whichever way it goes. Okay. All right. So what I want to do is I want to take that. So once I believe that's what I want for x to be, I just consider, well, I had 9 minus x squared, so I just plug in that. So if I drop a 3 sine theta in here, what happens? Well, 3 squared is 9, and then I get a sine squared of theta. Well, I can factor a 9 out of this, right? And what's the square root of 9?
3.
So that gives me 3 square root of 1 minus sine squared. And 1 minus sine squared is cosine squared. So now I have 3 square root of cosine squared, which is 3 times the cosine of theta, which I found a different way from my picture. Right? So it turns out there are multiple ways to attack these, but they usually end up in the same spot. So that's kind of the long way to do it. And this right here is the short way. Okay. It takes some getting used to. All right, now this is not too bad. We did that derivative the other day. We're going to do it again right now, but I got to reverse substitute. So that is another point of a challenge. So cosine squared, we have an identity for that. So I'm going to have 9 times the integral. The identity could be viewed as 1/2 times 1 plus the cosine of 2 theta. D theta.
Oh, that's the double angle.
This is the double angle formula or the half angle formula, depending on your perspective. Yeah. So that's an important formula. And then, so I have a factor of 9/2 I can pull out.
Wait, how'd you get 3 the other one and 9 in this one?
Excuse me, what?
How'd you get 3 the other one and 9 the other one? Because the other one you had 3 cosine, and this one you have 9.
Yeah, because I have 3 cosine times 3 cosine.
Oh, okay. I see.
So 3 times 3 is 9. Did I get that? Okay. So antiderivative for 1 with respect to theta. Theta, yeah. So tendency is to accidentally write x. Consider the variable we're using. So I have a parentheses theta. Okay, antiderivative of the cosine
Sine.
is the sine, but it's the sine of 2 theta, which meant there should have been a 2 sitting outside here, but it's not there. So we have to adjust with 1/2 there. And then we have a plus c. We'll deal with that later. So now I have an antiderivative, but it's with theta. That's like a different dimension, right? I need to come back to this dimension, so I get a reverse substitute to get x. What's up?
Go back to
Yeah, so the triangle helps me reverse substitute. Okay. So I'm just going to put this on another page with the triangle stuff, and then we'll break it down. So we've got right now antiderivative of 9/2 times theta plus 1/2 sine of 2 theta. And our substitution, our main one, is that, let's see, x is equal to 3 sine of theta, right? From our triangle. To solve that for theta, divide by 3. take the arc sine. So that's theta. Now, I have a slight problem. I can tell you what the sine of theta is, but I'm not sure what the sine of 2 theta is, but that's a double angle. What's the double angle formula for the sine?
1/2 1 plus sine.
Almost. No?
What is it?
Well, not really. That was way off. Yes,
Right.
Half the.
William?
2 sine theta cosine.
Correct. It's 2 sine theta cosine theta. Okay. So remember on our triangle, right? Our triangle had a here, had x there, and it had the square root down there. Theta's right here. So according to that triangle, the sine of theta is x over a, right? Opposite over hypotenuse. That's going to give me twice x over a. And then the cosine is the square root over a. Oh, a is 3. Sorry, I guess I should have wrote that down. I don't know why I wrote a there. Let's call it 3. Yes, it is 3. 3. So then I have the square root of 9 minus x squared over 3. So this right here gets plugged in for the sine, and this right here gets plugged in for theta. So let's do that and clean it up. So now I've got 9/2 parentheses, theta is the arc sine of x over 3 plus 1/2 times x over 3 times the square root of 9 minus x squared over 3.
So you just get rid of 2.
Oh, times 2. Thank you. I forgot about that.
Or
2 times. Yeah, so some things are going to clean up a little bit here. So the 2's are going to divide out. I've got to distribute this 9/2 through, and that's going to clean up things a little bit too. All right, so I'm just about ready for my final answer. So I'm going to get 9/2 times the arc sine of x over 3. The 2's canceled. 9 in the numerator, 9 in the denominator. Those guys are going to cancel. But I still have that 2 down there, so I get a plus x over 2 times the square root of 9 minus x squared. And now I'll throw in my plus c. So it turns out the antiderivative of a semicircle is quite the pain in the butt. It's a lot of work. So we had to wait till now to do it. We kind of ignored it until now.
Yeah.
What's that?
Can we continue to ignore it?
Yeah, so this is the idea of trig substitution. So the idea is if you see something that looks like a square root from the Pythagorean theorem, you can probably make a triangle to solve it.
So assignment is 20 questions.
Yeah, there's 20 questions.
And they're all going to take this long to do?
No.
So,
Or take longer?
Okay, so I'm just going to give you a summary of the whole thing, and we'll do one more. Okay. So
7 minutes.
trig substitution summary. There's basically 3 cases. So we just did the first case. So the first case is if you have something that looks like some number a squared minus x squared. Triangle version of that, if you put theta here, a has to be the hypotenuse because you're subtracting from it. X is better off as the opposite side than the adjacent side, which puts the square root on the bottom. So that leads to the substitution that x equals a sine theta, dx equals a cosine theta, theta, and the square root, sorry, pen troubles, is also a cosine theta. Black. Next case. Suppose instead it was x squared minus a squared. X squared minus a squared. Here's theta right there. X has to be what in this case? S is the hypotenuse. And then, let's see, where to the side that goes. I want the square root over here. And so A is going to go down there. So the easiest relationship to come up with here is just comparing x and a. So what functions compare x and a for trigonometry? Not tangent, tangent, cosine, or
Oh,
Whatever. Wait.
no, it's not co, it's
Secant.
R.
secant.
Secant.
Yeah. So the cosine is a over x. That puts x in the denominator. That makes me unhappy. Okay.
Oh.
Secant is the flip of that, x over a. So that one works out better. So it turns out the substitution here is x equals a secant. A secant, yeah.
A second.
Just a second.
The derivative of the secant is the
A
Secant.
secant tangent. So our dx in this case would be secant tangent times a. Just forgot my a. Secant theta, tangent of theta, and d theta, thank you. And the square root, what do you think the square root would get along with? Not secant, not sine. Well, it would do sine, but then it would be square root over x.
Would it be a secant tangent theta?
I would like maybe square root over a, which would be the tangent. Yeah, so it turns out the square root here is the tangent. So square root of x squared minus a squared in this triangle could be considered a tangent of theta.
This is weird. I don't like
Feels
it at
wrong.
all.
It is like trig.
First time either.
Yeah, this is trig on steroids.
That's what I was just thinking.
Okay. Guess what the last case is?
1 over
X
the
squared
square
plus
root.
a squared.
X squared plus a squared.
I mean, what happens
Yeah.
if there's something over?
If it's one, well, it doesn't matter where it is. If it's in the denominator or the numerator, that doesn't matter. So the bottom line is either it's a squared minus x squared, or it's x squared minus a squared, and then otherwise it's x squared plus a squared. Oh, what if it was a squared plus x squared?
It's the same thing.
It's the same thing. Thank you very much. Good job. Yeah, so there's only 3 cases with the Pythagorean theorem. Okay, so that's supposed to be a right triangle. There's
They're
my
both
right
parts.
angle.
There's so many parts to this one.
Here's theta. Okay. Where do things go? Let's see.
The two
X
sides on the
squared.
bottom, x squared equals the side.
X squared.
Don't want x down there,
That's the A.
so it's got to go over here. So a gets to go there, and because that's a plus, that has to be the hypotenuse. Yeah, x squared plus a squared. Okay, the easiest things to put together here are x and a. What function most easily puts together x and a?
Tangent.
Tangent, yeah. So our substitution here is x equals a tangent theta. Dx, derivative of tangent, secant squared. Okay, then we got to figure out what to do with that square root. So the easiest thing to put the square root together with is a. What do you think?
You forgot your D theta.
Oh, I forgot my d theta again. Thank you, d theta.
Cosine.
Cosine would be a over the square root.
Oh.
Secant is the square root in the top, yeah. So then the square root of x squared plus a squared is a secant theta. Yeah. It's in the-
picture.
Sure, you can take a picture of it. I published my notes,
Oh, yeah.
so you can just grab the PDF and just grab that page out of the PDF.
I don't know, you can't read the thetas. The thetas are a little
My
messy.
thetas are a little messy, yeah. I need a pen with better resolution.
I've noticed that the
A better
square
DPI.
root function,
Yeah,
the other side addition is always in the derivative.
isn't that, yes.
It's always marginal.
Yeah, so the square root and the derivative have a cosine, and the square root and the derivative have a tangent, the square root and the derivative have a secant, yeah.
You can guess which one is gonna be secant and.
Yeah. So then the trick is, aren't we good at taking derivatives of trig functions now?
Maybe.
Yeah.
From 3.2, we got pretty good at it.
Should be.
Yeah, are they still hard? Yeah, they're still hard. Okay, so we're out of time for fun with math. We'll do some more of this tomorrow. That's the cheat sheet for this section.
The assignment is like by
I
parts.
already told Gary, I was like, I need to go to college classes.
What's up?
So with the notes.
He's like, I'm not really too fucked
Yeah.
about my.
Are we gonna be able to put things on it, or are you
I
just gonna
had
have everything on?
I'm gonna open up another notes page for us to add to it.
Could we put this on the notes page?
Sure.
We should put